be discussing collaborative filtering, which comes under recommendation systems. And I will introduce singular value decomposition, how it can be used in collaborative filtering. Okay, so can you see the screen?
Yes, we can.
Okay. Yes. So once again, I thank organizers, and let's start the my topic, which is collaborative filtering and singular value decomposition. Students, especially if you have any difficulties, doubts regarding mathematics in this lecture, you can ask me in between or even after the this session. Okay. So what are the recommendations usually we get when we open, for example, if we open a YouTube and try to search video, when I prepared this lecture, obviously I went to YouTube to get more information. I searched singular value decomposition and collaborative filterings. So you will get lot of recommended videos on right side from your YouTube channel. Also, if you watch a movie or if you search a movie in Netflix, you will find similar movies watched by other users. Or if you want to buy a laptop from Amazon or Flipkart, once you search from Amazon or Flipkart, below you will see a lot of other recommendations, similar specifications having laptops. Even if you see news articles on Times of India, best 10, they will show it on top, something like that. So everywhere nowadays you will find recommendations, and which are very useful. Amazon claimed once that 70% of their purchases are through recommendations. Okay, so that much importance is there for recommendations, because when we have lot of possibilities, different options, giving the best recommendation is always a tedious task. Okay, so as I said, recommendations to watch related videos or movies, it will show, you will find these type of words: recommended items other customers often buy again, that you usually you will find in Amazon. Customers who viewed this item also viewed when you open Flipkart or Amazon, anything, or even Times of India. Okay, so these are all the different things one can get, and how we are getting is mainly because of this recommender systems, or you can call it recommendation systems. Okay, so we can call it simply RS. These are all the software tools and techniques providing suggestions for items to be of much use of a user. They are mainly based on different users predictions, or different users tastes, or different suppose one user have searched so many other things, based on that they will give the better recommendations which one can consider. As I said, suggestions related to various decision making process. For example, what items to buy, what musics to listen, or what online news article which we to suppose. For example, if you see Google feeding news from every mobile, even though app is same, but every user different types of news articles will come as a recommendation. So mainly these recommendations completely personalized to a user. So depending on user taste, recommendations will be different for different persons, even though the app is same. For example, you take Google app, Play Store, or if you take YouTube, even though you are searching using same app, but recommendations will be there for different people, different recommendations will come. Okay. These are all the, as I said, primary application of recommendation system is finding a relation between users and products in order to maximize the user experience. Okay, fine. When it comes to some popular approaches used in this recommender systems is I can mainly say two. One is content based filtering and the other one is collaborative filtering. So this content based filtering, I'll just take 2-3 minutes to explain with an example, and then we go little more time in discussion with collaborative filtering. After that we'll move to singular value decomposition. Okay. So this content based filtering is mainly based on one user and various items he has already interested. So it is one can say based on a description of the item and a record of the user preferences. Okay, so in this content based filtering, we are not bothering about what other users are liking or giving rating for that particular some of the items. So this is mainly based on the particular user which he searched in different places with different items. Based on that, this content based filtering will be working. It is best suited when there is a sufficient information available on the items but not on the users. Okay, suppose if you say you want to purchase a laptop, if you want to buy from a store where a lot of information is available and in this especially related to laptops, then this is going to work better. Okay, fine. Let's quickly see one simple example. It doesn't take much time. For example, you assume that you have this Nikhil is a person. I give due respect to the images whichever I have taken from internet. Okay, so if you consider this person, he is a Nikhil, which he has given ratings for 3 movies. So based on this information available, we would like to give recommendations to this particular person again, which movies he can watch. Okay, so he has given two good ratings for this 2 movies, and the Toy Story he has given bad rating. So he didn't like this movie at all. So what we can do here is we can understand from this information whatever we have for this user is that he like action movies. Okay, user likes action movies and he doesn't like animation or children type of movies. Okay, so based on this one, we can have a rating system. You can see here the rating system 0 we will put it for animation related, and if we go right side, the action movie related, because he liked it, so we are giving more rating to action at, for example, 10. And when it comes to children's, because he didn't like children's gender movies, so we are giving negative ratings for this particular user because it is content based. Okay, now if you see this, you take this, we can make it as a vector in order of action, animation and children. To this Nikhil we can give a rating, I mean this 9 0 then -6. So that means he like we are given 9 for action movies, 0 for animation and -6 for children related. Okay, now with this one we can for example, now you take 2 movies. One is even though it is already verified, so you take Toy Story. Toy Story is 0 1 1. Okay, then just a second. This is for Toy Story. Okay, and you take the other one is suppose Star Wars. So Star Wars because the because it is related to action, so we have given it is binary. If it involves then 1, otherwise it is 0. So it involves action, it is not animated or it is not children oriented. So 1 0 0 is the vector rating for this Star Wars. Okay, now how we can rate in this content based movie recommendation is simply taking the dot product of this user's interest with the given whatever we want to suggest or not. So for example, you take this 9 0 -6. Okay, then you dot product with this Toy Story which is 0 1 1. Obviously we get -6 -0.6. Okay, sorry, not -0.6, this is -6. Okay, right. Then if you whereas if you take the dot product with this Star Wars which is 9, okay, 0 then -6, if you take this one, obviously we get rating as 9. So we can recommend the Star Wars to this person, a particular user Nikhil, and you can see that we even if we don't know this Toy Store, this we got -6. So obviously we don't recommend, and it is matching with this already whatever he has given bad rating. Okay, so this is content based movie recommendation, especially the user which already he watched and he has given ratings. Based on those ratings, one can give which new movies he can watch in future. Okay, fine. Now let's go to collaborative filtering. See, what is the other type of filtering is collaborative filtering, which usually the word itself suggests the basic idea is using the interactions and data collected by the system from other users. Okay, so here mainly the tastes of other users. The collaborative filtering depends on the set of collection of users which are similar to this particular given person. So assume that we want to give a rating to related to this person A, right? Now how collaborative filtering works is we will find the similar users, okay, then based on the tastes of similar users or based on the recommendations whatever they have given for these similar users, we will recommend to this Mr. A. We will recommend to this Mr. A based on the recommendations of the users which are similar to the person A or Mr. A, right? But this collaborative filtering, one can again have it in two different ways. One is user to user and item to item. What is meant by user to user? For example, this similar users like a movie, then we will recommend that movie to that person. Whereas item to item is if you want to recommend one item, then we will find the similar items, okay, which these users have liked, okay. And most of the time this item to item works well because users choice may vary depending on different items, okay. But the procedure for user to user filtering and item to item filtering is same, okay. So if we just quickly summarize what is this collaborative filtering means, it depends on the choices of the users, so-called similar users, okay. And it is also believed that in previous these people have liked it, so in future also they will be liking the same thing. Based on that we are going to give these recommendations, okay, fine. One may ask, if you take this Mr. A and find the, we will find this set, we will call it this as n, set of n n is the set of users, okay, which are similar to that that of this Mr. A. Now we want to predict the ratings based on the ratings of these users which belongs to this set n, right? So if we know the similar users, then obviously we can have a mechanism how they have given the ratings. Based on that ratings we can give the rating. So it is not at all a difficult one, but what is little difficult or challenging is how we can identify the similar users is the most important or challenging thing, is identifying similar users, okay. So we'll see quickly one or two different methods how we can identify and which will be the better thing, okay. For that, to consider a table consisting of, we have 4 users, so user 1, user 2, user 3 and user 4, and we have, so 4 users we have and 6 this movies we have denoted, okay, as M1, M2, 7 movies, sorry, okay, 7 movies we have, and each one have given some ratings to some movies and they have not given ratings to many. You can see here there are so many blanks are there, right? So if we write Rx, this if you call it as this Rx, that means it is RA, movie ratings given by A for movie M1 and M4 and M5, okay. Then similarly you consider RB, RC, RD. Then we want to find the similarity metric. You can denote this by sim x comma y, okay. So we want to find the similarity between the user X and the user Y. For example, similarity between A and B we want to find. Similarly, similarity between A and C, like that, right? But if you see here in this table, whatever we have, this A and B, okay, A and B only rated this movie 1 in common. For example, B has rated movie 2 and movie 3, and whereas A is rated movie 4 as well as 5, which B is not rated, okay. So how we can find whether they are similar users or not? Whatever methodology we apply, what should be the output? Output should be the close to the our intuition, okay, intuition. For example, you say that even though they have rated only one picture common, but they have rated very closely 4 and 5, so almost very good rating they have given, Okay, whereas if you see A and C, even though they have rated two movies in common, okay, these two they have rated in common, but their rating is completely opposite. For example, he has given 5, whereas he has given 2. When he has given 1, he has given 4. Okay, so extremely opposite. So we should not think that A and C similarity is better than similarity of A and B. Okay, so in that sense, we have to design our algorithm. So our intuition should be similarity of A and B should be strictly greater than similarity of A and C, right? So how we do this? There is a methodology called Jacquard similarity, which is obviously very simple. What it says is that if we want to find similarity between A and B, what you do is this is the formula, how many they have rated in common and divided by how many they have rated total. So intersection upon union. For example, if you use this formula, what we get here is similarity of A and B. You can easily calculate because they have rated only one in common and they have together given 5 movies rating. Okay, because one is common there. So then similarity of A and C, if you calculate, because they have given these 2 movies in common and again they have this 2, 3, 4, right? So this is 2, 1, 4. Okay. 2 to 4. This comes under 1 upon 2, which is, you can see that here similarity of A comma C in this example, in this methodology, we are getting bigger than similarity of A comma B. Okay, which is not close to our intuition. So we don't take this Jacquard similarity, but we go for the other one, which is called cosine similarity. Okay, that means angle between these two vectors, right? If you consider these ratings as vectors, then we will try to find the angle between them, how close they are. So the angle is, if angle is smaller, then obviously they are closer and so on, right? So for this, the cosine angle between these two vectors RA and RB. Okay, and obviously that whoever know about mathematics, they may be knowing this is numerator it will be dot product and in denominator their product of their lengths. Okay, so if you calculate using this, what we get here is similarity of A comma B we get here as 0.38 and similarity of A comma C is 0.32. Even though here this similarity is of A comma B is strictly bigger than similarity of A comma C, but not much far. It is very, very similar. But according to ratings, if we see, they are not matching that much closer, right? So there is a small modification one can go with, which is called centered cosine similarity. So what is this centered cosine similarity? Only difference is when we if we go back here, when we calculate this dot product, obviously what we want to give this as a vector 4 0 0 5 1 0 0. So you can put it zeros here, okay, and you can put it zeros here, then calculate the dot product. Okay, so when we are giving 0 here, that means we are giving almost, even without watching, we are giving 0 rating for many things, right? That may be the one reason. So to overcome this, instead of giving 0 values, we'll try to normalize this rankings. Okay, so that is the idea. We will try to normalize ratings by subtracting row mean. What is meant by that? For example, here what is the row mean? Row wise average is nothing but 4 plus 5 9 10. So this is 10 by 3. Here it is 14 by 3. Okay, in this way you can calculate row wise mean. Then you have to subtract this 4 minus 10 upon 3. Okay, so 4 minus 10 upon 3, then here you don't need to do, here you have to do it. This is again 10 upon 5 minus 10 by 3, right? 1 minus 10 by 3. Okay, if you do this for every entry, then we get the better rankings. You can see on this table that the earlier it was ranking as 4, now it is 2 upon 3, then it is 5 by 3. Now if you see this minus 7 by 3, it is in negative. Okay, and if you sum these 3 values, what you get here is 0. Okay, 2 plus 5 minus 7 by 3, which is 0, right? Similarly here also if you sum, okay, sum is 0, right? That means actually we have normalized, or we have centered the rating of any user to average rating as 0, okay? And anything positive we can understand is that this movie is good, okay? And if it is negative, then that movie is bad, right? According to his taste, right? So what is the advantage of this one is that we have controlled the users upon their ratings, okay, instead of having exactly 5 then 2 1 and so on. So here we have normalized the ratings, and after this if we calculate using the same formula which we have calculated earlier, we got similarity between A and B is 0.09, and whereas similarity between A and C is minus 0. So it is in negative minus 0.56, okay? So that itself says that the similarity of A and B is better than similarity of A and C. So we can say that B is similar to A when you compare to C, right? Fine. So now after doing all these things, we this centered cosine similarity and finding the who are the neighbors or who are the similar users to that given particular person, then what we do here is how you can rate the predictions, okay? So we want to predict user of X and particular movie, you can call it suppose I, okay? This is small letter I, that you denote by this RXI, right? So we want to calculate this, and you take n with the set of k users which we have just calculated using previous ones, right? Then if we find this k users, the one formula we can simple obvious formula we can do is average ranking of all k users, because all these k users we have identified as similar users. So whatever ratings they have given, we will take the average and we will give that. So that is one way. And when we calculate this comes around, which I have calculated earlier, I think it which comes around 4. So based on that rating, if we calculate, we get rating 4. Let me go back here, okay? Or whatever, suppose we want to rate to this particular movie 2, okay? This we want to rate it. We want to rate movie 2 of this user A, and B and C we have seen they are similar persons. So B and D, suppose whoever rated this B and D, so you take 5 and 3, right? Then take their values and you take the average of that one, right? But the problem in the above formula is that we are not considering how much similar they are. Whatever these values are there, we are not considering those values when we are calculating the ranking. We have just calculated who are the neighbors. After that, we are only worried about their ranking, whatever ranking we got. Based on that, we have calculated average ranking, which may not sound good, because we have completely forgotten how close they are, even though they are similar, but how strongly they are agreeing on a particular item, right? For that, we can have a better formula, which we can call it as weighted average rankings, which we involve this SXY, which is nothing but the similarity of X comma Y. So between two users, whatever similarity value we are getting, we are multiplying to that and taking the average of that one, okay? With this rating, if you do it, for example, if you want to do it here, how much this M2 rating we can give for this user A. So take this C and whatever it is there, based on the calculation, if we do it, what we get is around 2.6 rating. We get the 2.6 rating for that particular movie, okay? And calculations and all, I'll just skip those things. You can go through it, and if at all any calculation mistakes are there, you can correct also, okay? This is about collaborative filtering, which we have seen so far. Now it comes to singular value decomposition. where actual mathematics involves. So what is this singular value decomposition? Is a method, of course everybody know it from linear algebra. It has been usually used for dimensionality reduction, okay, technique in machine learning, but this can also be used when it comes to this recommender system. The SVD can be used as a collaborative filtering technique, okay. We'll see how we can do it. The main thing one can understanding is that this SVD is a matrix factorization technique which reduces the number of data sets by reducing the space dimension from n to k. That means from n dimension it reduces to k dimension, which many times is very useful. Many people, that means when you have huge data, it is always good to reduce without losing much information, okay. So at all those places this SVD plays very crucial role. As I said, it uses matrix structure, okay, where so you have this one where each row represents users, okay, and where each column represents some these items. For example, when you take movies, these users and items are nothing but movies, okay. Then whatever entries we have here, those entries are nothing but those entries whatever we are having here, they are the ratings given by that particular user to that particular movie, okay, fine. What is this singular value decomposition? Is if you take a matrix A is any real valued matrix of size n by d, then A can be written as, so A can be written as U times sigma times V transpose, okay, where even though your U is an n by n matrix and sigma is n by d matrix and V is, or V transpose is d square matrix, but the beauty in singular value decomposition is that even though your U is look like n by n, actually it gives U which is n upon r. That means you can reduce this to n upon r, where r is nothing but rank of the given matrix A, okay. That means if you understand this whatever rows are there, that is not reduced, okay. So you can call it, this is user matrix, user, okay. What is reduced is this much part we have eliminated, okay, only this much part we are considering, right. That means the rows are as it is, okay, but the information which is not relevant to the movies, for example, if you take users and movies, then this much part is removed. That means so many movies information is not necessary, so it removes that and gives only the useful information, okay. Whereas it comes to this sigma, so this sigma which is called it is actually diagonal matrix. That means only diagonal entries are non-zero, remaining all entries are 0, okay. And this is very useful in deciding the strengths of whatever you are talking about, those concepts, okay. Then later it comes to V. So if you see that in V, this much columns information is not necessary, or it can be removed, or we can neglect this, only consider this much information. That means here all movies information is there, but only users information is reduced, okay. So you can call it this U as user to whatever you can call it, movies or items, but whereas this one is called movies to items, right. And also the beauty of this singular value decomposition is that in this factorization, this U and V are orthogonal matrices. That means when you take U and U transpose, it is equal to identity matrix. Similarly, V and V transpose, okay, they are orthogonal matrix, and this U is called as left singular vectors, and this sigma which is called singular values, whatever they are, there you can call it as strengths of our concepts, and the V is called right singular vectors, okay. So this is the basic idea. Given any matrix A, we can decompose this matrix or we can factorize this matrix into three different things: U, then sigma, and V transpose. Okay, where U and V are orthogonal matrices. This sigma is a diagonal matrix, which based on this sigma, for example, here if it is R by R, then only we will consider first R columns, and this singular value, this whatever sigma we have, if you take any matrix A, which is a real matrix, it can be always decomposed into the singular value decomposition form, which we have written as A is equal to U sigma V transpose. Okay, right? As I said, all three matrices are unique. So this unique plays very important role in many places. Whenever you have uniqueness, then many advantages having. Okay, and this sigma is a matrix which is diagonal matrix, and those entries you can denote by sigma 1, sigma 2, sigma 3, and so on. Okay, so therefore sigma 1 is the highest values, then sigma 2, then sigma 3, and so on, but they are all greater than or equal to 0. Okay. Fine. Now with this short introduction to this singular value decomposition, of course, if you give any matrix as a data scientist, even Python, or if you use MATLAB, anything, it will decompose that given matrix into this U, sigma, and V. Okay. But what is important is you should know this sigma is, and even though rank is R, but that means you will have up to sigma power R, this sigma R, but after some time you will see an example, these sigma values are very, very minimal. So we can consider them as noise, and we can forget about those things, and corresponding rows and columns only we can consider. Okay, that comes under dimensional reduction and so on. Okay, let's quickly take an example of giving ratings, movie ratings. Okay, so if you take this, I have taken again to skip the calculation part and all, I have taken this images or whatever information which already calculated by someone, and to understand better, I have taken as it is. Okay, so if you take this matrix, rating matrix, you have users. Okay, user 1, user 2, user 3, and so on. Then columns are nothing but different movie names. Okay, matrix, align, and so on, right? And here this users somehow in this example at least have been classified into 2 or 3 different parts. You can say users liking the sci-fi movies, and users liking romance. And there are, of course, you can see there are something you can call it, this is in different category. Some are liking here as well as here. Okay. So now if we want to apply this SVD and find if you apply any algorithm and so on, then what we get here is this one. So this is our matrix U, and this is our matrix sigma, and this is our matrix V, or you can call it V transpose. Okay. So any computer algorithm which knows, for example, Python surprise is there, you can use that, and MATLAB also, it can give the SVD of given any real matrix. Okay. If you observe here, there are many zeros are there. Okay, you can assume that they are all missing values. Okay, of course, there are a lot of ways you can fill these missing values, and once you fill the missing values, then you can apply SVD and so on, right? Or you can directly take it as zeros and then you start applying SVD. That is the basic first method you can understand, right? So what is this U says? Because you now, to understand better, you take this sigma. In this sigma, what we have here is 3 singular values we have, but when you compare to these 2, the third one is very, very less. So we will omit this one, and we will consider only these 2 singular values for better understanding. Okay, that means we are considering only sigma 1 and sigma 2, and we are not considering sigma 3. Maybe we can consider as a noise, and we can forget, because sigma 3 is very, very small compared to these 2. Okay, 1.3 is very, very small, right? That means corresponding to this 2 by 2 matrix, whatever we are having, we will take these 2 columns here. Okay, and then we will consider these 2 rows here for our understanding, right? So you can see here this first one, if you consider if I go to next one, so you can see here. Just a second. So these are all users. All users are there, but only movies have been reduced and combined to, you can call it, say suppose this is sci-fi movies, okay, and the other one which is related to, you can call it romance, okay, right, and the other one which we neglect even though they are of different type of things, right. Similarly here, this corresponds to these two all movies. So these movies whatever we are having here, they are having these characterizations in terms of these things, right. Okay. Now how we give, for example, we want to find users who likes the matrix movie called Matrix. So we want to find users are say suppose someone someone already liked a Matrix movie. Now we want to find the users which are similar, okay, so that we can give the ratings for missing things, right. So for this, you take, suppose, say call it a user which he likes this matrix. So he has given 5, we are giving 5 ratings, which is the highest, okay, and remaining all we have taken 0. So we have a user now who like this matrix movie and nothing else, right. Now we want to find if at all we want to give for example some rating here and here, right, because he has not given that rating, then we want to find similar users corresponding to this user Q. For that, what we do, we take this Q and this is our vector V, okay, this is related to the movies. So we will try to find the inner product Q times Vi. Remember, we don't take all these 3, we take only these 2 entries because of this sigma, right, and this is our U. Okay, so this is V or V transpose, you can call it. We will try to find the inner product Q times, this is V1 and this is V2, okay. So if we find this, then we get this matrix, that value in which is related to SkyPy, and the other one is which is very negligible, so we forget about this. So he belongs to this SkyPy concept, right. Now we will try to find the other person. For example, take this D, okay, whose ranking matrix we have given as 0, 4, 5, 0, 0. So and we will try to find what is his space value matrix. That again, if we try to multiply this Q times V or VIs, what we get here is this one. Again, you see that he also belongs to, this person also belongs to SkyPy concept related movies, right. So if you observe, the conclusion is that this is user Q and the other person D is also another user, okay. When you see their initial ratings, you feel at least we get an intuition that they are not at all similar, 0 ratings in common, okay. But when it apply to this singular value decomposition, what we get here is that they are having some similarities in terms of this SkyPy related movies, because the one person we got 5.2, the other person got 2.8. So we cannot neglect, because they are having close similarity in terms of this SkyPy concept. So we can, using this singular value decomposition, we can say that this D is you can say that he is similar, okay, to the user Q, right. Even though from just by looking their ratings matrix, we cannot conclude anything, but singular value decomposition gives better predictions, okay. Some of the good things, if I would like to say, is this is very good in as I say, optimal low rank approximation by reducing noise and all. But what is not good is that this singular vectors, whichever example we have considered here earlier, this we have already factorized into different portions, like users, they are all classified into 2 or 3 categories, but that may not be possible here. So these singular vectors may be linear combination of all different types of gender, whatever we have having. The other thing which one should, this lack of sparsity, that means in this factorization, A is equal to U sigma V transpose, even though this A has is a sparse, matrix. That means many items are missing, so only few entries are there. But this U and V, they're dense in terms of values. Okay, for example, if you see this example, even you have so many zeros here, but none of entries are having zero entries here, right? So technical terms, you all people know better. It requires a lot of computations. So there are some modifications to this SVD called SVD plus plus and R reduction SVD and so on. Okay, reduced SVD. But I'll because my time is about to over, I'll stop here. And as I said, these are some of the references which I have taken while preparing this lecture. So I'll stop with this and hello.
Yes, Dr. Surendra, yes.
Yeah, I'll stop sharing my screen so that.
Okay. Well, thank you for your wonderful talks. It was very insightful, even though it was technically involved, but I hope some people do have some questions, and now we are open to questions. If anyone has questions, please raise your hands, and we'll provide you or give you this privilege to unmute yourself and ask questions.
Surendra.
Yes, sir.
Sorry. Yes, hello, sir. I'll ask.
Okay. Sorry. Surendra, it was a very nice talk and it was very informative, quite nice. I would like to know whether this SVD can be used for categorical values. So you have these, those values 5 and within the range, but if we have only zeros and 1, can we use this SVD?
Yeah, as far as I know, this SVD gives factorization. So whatever matrix we have, but because of factorization, it will remove unnecessary things. For example, if you see that matrix U, it is basically a cylinder type. Okay, many things, unnecessary things have been removed from that U, and when you see V, it is like horizontal one. Okay, so it is always whatever matrix it may be, it is always gives better. That means it removes the noise and gives the surroundings where you have better predictions.
And what I could understand that when you were showing those examples, like somebody have rated some movies and whether you want to rate them, predict them as a sci-fi lover or romantic movie lover or something like that. So that's the part you are doing the prediction, right?
Yes.
Okay. So you are predicting.
We are multiplying with the matrix Q, which is a user one, then with those VIs, Q times VI dot product.
Okay. I'm done. Thank you.
Okay, Surendra, I have a question because you gave a nice example of this filtering and to give the rating and use the rating to identify which class of this movie will particular fall. So my idea is that this is the only factor that will contribute in that overall classification, or there could be some other factors also?
Yeah, there are other factors. For example, we can have instead of having this A or U, you can have take K. K is anything less than R. R is a rank. So you just like in this example, even though sigma has 3 singular values, we have considered only first 2 singular values. So when it is practically your sigma is a huge matrix, then we want to give predictions. Instead of taking R, you can have a user demand K value. Then based on that, you have separate UK and then sigma K and VK transpose. The correspondingly you have AK. And based on that, we have a better approximations.
Okay. Thank you, Surendra.
Yes, thank you, Surendra. So, yeah, I had one small question, so it's not very deep, but I would ask it anyway. So, why do you think these 3 matrices need to be unique while performing this SVD?
See, the problem is if we have 2 different representations, okay, then there we have omitted some other unnecessary things. Okay, suppose you call it U1 and V1 and U2
Right.
and V2. If they are different, so there is a loss of chance that you will be missing some actual predictions. If U1 is different from U2, then we are actually removing many things from that, just like a cylinder. So many columns we are ignoring from U. So if you have U1 and U2, so there is a high chance that you will be missing the persons which are actually given proper predictions. So because of this uniqueness, we can go ahead without thinking second thought.
Okay. All right. Well, thank you, Surendra, for your talk.
Thank you, sir. Thank you, Alok, sir.
Any students would like to ask questions? We have 1 minute if you want to ask. So it seems like there are no more questions. So thank you, Surendra, once again.
Yes, sir.
Thank you. Thank you.
Yes.
Chandan, are you here?
Yes, I'm here.